Good morning.
Anna.
Good morning.
Good morning. Jeff. Okay, ladies. Good morning and welcome. Okay, girls. So first of all, yes, okay, let's just talk a little bit about sorry, quality assurance. Okay. And what that means is going to be is okay, a procedure that routinely is okay will be run at your facilities. Mainly just okay to ensure that the machines are working optimally. Okay. And the reason that that is going to be as okay important is that okay, as you can see, okay, you'll be able to just okay rely upon the scannings that you're doing. Okay. In case that okay, as you say, mean is okay, run a test on the machine and is found not to be optimally scanning. Accordingly, as okay, it's going to be the job of the technical department to fix that issue. You may, as okay, while doing your quality assurance scannings, adjust on the settings on the machine. Okay. What they mainly as okay use for what we call as okay quality assurance is going to be as okay a fixed model. Okay, this is not going to be something that you do on a patient. But what they mainly as okay use is what we will call phantoms. And phantom is mainly as okay bigger or smaller as okay block of what they call ballistic gel. And what they have done is okay, yes, run different structures or place different structures at different distances in that phantom. And what you mainly as okay will see as you or do as we see in the video is compare the image that you scan to to what is going to be displayed at the phantom. Now, ideally, speaking, they should be pretty much as exactly the same. But as a couple of % off or so on so is still acceptable as you can say as good report for a quality assurance. Okay. Now, how frequently is that going to be performed? That's something that, okay, as your facility may determine. They may say, well, okay, every first Monday of the month, the first 2 hours, we're not going to be checking in patients because that's when we're going to just, okay, do our quality assurance, something like that. Okay, so it's in many places, okay, going to be something that is going to just, okay, routinely being performed. Is that clear? Okay, so mainly as okay, you can say as okay, just a fine tuning or yes, okay, checking upon yes, okay, the reliability of your equipments. Any questions at this moment? No?
No.
Okay. That was not optimal. Why? Why is that? Okay. Hmm. Okay. So let's see. You guys can see where it says cardiovascular sales.
Yes.
Okay, good.
Hello, and welcome to another 2-minute tip.
Okay, girls. This little dude here, that's ultrasound machine. So you actually can see that, okay, as you have what you can call as, okay, portable ultrasound machines available as well. Clear, which means that's okay, just like, okay, it is at the same size of a regular standard. Yes, okay, you can say laptop. Okay, but you can see, yes, okay, you got all your functions. You have your keyboards, different function keys. Well, okay, this for instance, okay, is your TGC. You can say it's okay, different modes. That's your mouse, things like that. Okay, so pretty much okay, it's everything that you need. Okay, and some of you will say, well, what is this? Well, this is the Phantom. Okay. So this is the phantom. It's mainly as okay going to it's okay this block off. As you say, it's okay ballistic gel. And all these drawings here are as okay these darts, exact shades here. That mainly as okay is going to as okay, or that's mainly as okay the shades that you ideally as okay will be seeing on your screen. For instance, okay, if you're scanning here, you ideally as okay should be able to see this. And of course, that's okay, greater and greater and greater and greater depths. Likewise, these and so on. So okay, so mainly as okay, just scanning as long as okay your phantom and what you actually as okay should be able to see is these structures. And what you will see is that they also do measurements to determine whether okay the distance between let's say it's okay this and this here is the same as what you've seen on the scan. Okay, so they may yes okay will have okay some yes okay specific scale, but okay yes a distance on this one here is going to be yes okay on your scanning. Okay, so that's pretty much okay how you run a what you can call is okay quality assurance, and this is okay as a regular yes okay type of phantom. Most yes okay facilities will have yes okay their own phantoms, which mainly is going to be just like this one here. Okay, okay, girls. So yes okay, this here is okay that's your portable ultrasound system, and well okay this fellow here that's the phantom. Okay, let's just continue.
Today we're going to go over the basic use, what it is, and why you would want to use a phantom. This is one of the most basic phantoms that you'll find. There's a wide variety of phantoms used for ultrasound, and in general a phantom just means it's something that's taken place of a body that you can image. The real advantages of that is it gives you something that's consistent and stable, that you're looking at the same thing each time. When you make photographs of a phantom image on a particular ultrasound machine with a particular transducer, you can then use that as a reference photo to go back over time and look and find out if the image has changed, if the photography has changed, or in fact if there's problems with the system that were not there previously. And that's one of the main features, is actually to document it. The phantom is used primarily for Q&A and assisting in troubleshooting with the ultrasound image or a probe issue. It provides constant and reproducible images of known targets and distances, and it allows you to document the system performance over time. The phantom itself physically is made up of a variety of items. The most common is one that's similar to this. It's made of something like a ballistic gel. It looks like a large rubber block. And the second most common phantom is probably the tissue equivalency phantom, that is actually filled inside with a gelatin type material that, if you cut it open and look, has the appearance of being filled with graphite particles, so that it actually mimics the appearance of a liver when you're doing an exam on it. All phantom has to transmit the ultrasound signal at the same velocity as it does through the body in order to make measurements correct and have the image correct. And also it has to have the same amount of attenuation as the body, meaning as the ultrasound signal goes in, it's attenuated and it loses signal as it goes down and bounces back up again, and it has to lose that signal at roughly the same rate as it does in the body. This phantom, you can see, it's got a diagram, like all of them do on the outside, showing you what's inside the phantom. Here you'll see a series of rods that are going from light to dark, and they appear as circles on here. In fact, that's actually a plexiglass rod going sideways through the image this direction, and I'll be able to show you that to you when we're scanning. Over here, this is the same thing, only these rods are all clear. These vary in their density. Over on this side, what looks like pins as you scan the image are actually, again, wires, very thin 1mm wires, typically going through the system this way. When you scan in the plane this direction, what you get is an image that looks just like this. And these items are all put on here to do something different. We're going to scan and see each one of these in a moment, but I'm just going to describe what we have on here. The primary functions of the phantom are to show axial and lateral resolution. So it wants to show how good your resolution is, going in the direction of the beam, and also sideways. This type of wire marker display is particularly good for that. The wires get progressively closer as they come down and curve and turn from axial to lateral. and you'll look at the image and we'll see how closely these wires can be and still be seen as a separate and distinct echo on the monitor. That's what the goal is for checking the axial and lateral resolution. In addition to that, we're going to check both the axial and the lateral measurements. When you go to make a measurement, whether it's to look at the size of a particular gland, to see the size of an occlusion, or anything else, you want to know that that measurement's accurate. So there's wire markers at fixed distances in here, and they're labeled on here. We can go in, we'll actually make a measurement with the system, and see if it matches up to that. Contrast resolution is what you can see right over here. It wants to find out how well you can see changes in density, not just a change of a size of an object. There's only 6 steps across here, but you can actually watch it go from being able to transmit all the echoes through it, it'll be perfectly clear, to passing the echoes and not being able to see those on the bottom. And you want to be able to see that you've got nice gradation through here. These are the same size, these represent cyst, and these are hollow plexiglass rods again, and they're clear as you look at them with the ultrasound. So what you're trying to do is find out how small of an object. You can still see the difference in the contrast between the surrounding tissue and, say, a cyst, and you also want to make sure that that cyst is clear. It doesn't have a lot of echoes in it, and that's what each one of these are for. You also have another set that shows you near the near field, so you can take a look at a high-frequency probe and see how well it's seeing in the near field, and if it can see down to the 1 centimeter marker. In a lot of cases with a transducer that's somewhat obliterated, and you'd use something like a standoff pad to see better there. That's what this is for, to evaluate your image and document it. And now let me show you what each one of these look like on the monitor. Put the transducer on top of the phantom. Have it covered with gel to make good contact. And you'll see a representation on the monitor, very similar to what you're looking at here. You'll see that these are actually very small 1 millimeter pins or wires going across there. And when you look at your resolution, you're looking for axial resolution along the axis of the plane.
So girls, this is your axial resolution. Okay, that's why we also call it depth resolution. Okay, whereas this here, that will represent, you can say it's okay, your lateral resolution. Okay, or even if you compare this to this, you can say it's okay, good lateral resolution. Down here is okay, the lateral resolution gets, that's okay, a little bit degraded if you want to put it that way. Okay, but that's okay, that's okay in accordance to, that's okay, your that's okay, your lateral resolution on the in the phantom. Okay.
And lateral resolution. And what you can see is that the axial resolution is quite good. Very small in this direction. Lateral resolution is not so good. It's spreading out. That's just a function of the type of transducer I have here. I have a high frequency curved array transducer. The curved array spreads out farther, just like the spokes of a bicycle, and you'll get worse resolution on there. If I have a high-frequency linear transducer, you'll see something very, very much like you're looking at here. Very distinct pinpoints. And this is what you're looking at. That's not good or bad. It's a function of the system and transducer combination, as well as things like focus and depth. What you would do is take a photograph of this, and over time you'd be able to tell if that image is staying the same, if you're losing resolution in one direction or the other, or even if you had dropout along the area somewhere.
Now, girls, you say you may take a photograph of this. That doesn't mean that you take out your cell phone or something like that, okay, and take a photo of it. It mainly will mean that, okay, you save that photograph on the system. Okay, there may be a folder on your computers, not computers, your ultrasound systems that goes, yes, okay, under what you can call it, quality assurance. Where you mean is, okay, we'll just save the images that you scan on today's date, and that quality assurance being performed. So that, okay, not only do you have pictures to go and back and look at for, okay, as okay, for a source of reference, but that it also is, okay, is documented that, okay, yes, on September 11th, 2023, yes, okay, we were due for, okay, as a quality assurance or whatsoever, and okay, as it was actually done and performed. So whether you have, okay, as good quality assurance reports or bad quality assurance reports, images needs to be saved. Okay, girls?
That's for axial and lateral resolution. For axial and lateral measurements, we'll do right here. Let me freeze. Looking at the lines down here are matching up the lines coming down here. They're 1 centimeter apart, and they start at a fixed surface fixed distance from the surface. That changes a little bit as you push up and down here. That'll move. So typically, what you'll want to do is not measure from the surface, but measure between a series of dots on here.
No. Okay, sorry, Ross.
Measure from the surface, but measure between a series of dots on here.
Now, the reason that you didn't see any movement in the image here was because the image was frozen. Okay, as he is pressed with the transducer. Had the image not been frozen, then as you might have seen, as a slight bouncing of the transducer up here. Okay, so okay, ladies, let's just okay, goes. Okay, so you can see that it says cardiovascular status again.
Yes.
Okay, good.
Go back and I turn on the caliper. I can move that as close as I can to the center, or just move it to an edge. All you want to do is make sure you can duplicate it. Then I'll hit my second caliper. I'll move that down, say at least 3 centimeters. I'll move it to the bottom there again. Get it right below. Hit set. Where's my measurement? Oh, here we go. 2.98 centimeters.
So that's
We're expecting 3 centimeters. That's very good measurement. So that's showing that our axial measurements are right on. I'll then move over and we'll get a measurement where we have like this one right here where it's measuring crosswise. Freeze.
Which you'll
and
probably
again,
see here.
because the resolution in that direction is not as good, what you'll find is that it's harder to make the measurement. What you'll end up doing is making an educated guess that it's center to center. And it's measuring 2.03, and that's a 2 centimeter distance up here, 4.5, and so again, that's very accurate. You could do the math on the percentage, but it's a very good measurement, and it shows it's not off, and that's critical, and you want to document that. The other thing that you're documenting, besides the axial and lateral resolution, the axial and lateral measurement, is you're looking for uniformity of the image. That's another thing a phantom is good at showing you. That's a nice uniform image. If it got darker down here, then brighter here, and that would show you that you either needed to adjust your settings for your TGC controls, for example, or that you had a problem with the focusing on the system itself. If you looked in the near field and you had dark dropout, that would be indicating you've got an issue with the transducer and likely dead crystals. You could easily put another transducer on, the same type of probe, same imaging setup, scan the phantom, and you'd readily be able to tell if that was your transducer that was at issue or not. Looking in the near field, I don't have that burned bright like you would on some probes, especially deeper probes. This high frequency probe has a nice clear near field on there. When you're doing something like looking for a breast cyst to find out if you're going to do a biopsy or not, that's what you want to be able to see, is a nice clear near field. Going back over to this side, this transducer is a higher frequency and we're not going to be able to get the depth that we probably want. What you'd like to be able to do is see a multitude of the rods running down.
Okay, guys, there's something that I want to show you here. You can probably see this dude here, right? Okay, which would most likely has been this one here. Okay, okay, applied reflection. Okay, but what you actually see here is what we later on, yes, okay, in okay, as chapter 21 we refer to as shadowing. Okay, so that's going to be as okay an artifact, but that's pretty much okay as how it is going to be looking. Okay, so that may tell us okay, it's a bit about it's okay the nature of this structure here. You know.
On the side and be able to see him go from lighter to darker all the way down. A higher frequency transducer will not go as deep in the body as a lower frequency transducer, and that's why we're not able to see these plexiglass rods down here very well. If I get off to the side, I can see him better, and with the linear transducer, I would see him a little bit better as well. But move over here to the cyst. Now this is supposed to be duplicating a cyst, and if it's a true cyst, this is going to be very dark and black. It's not going to have a lot of noise in the middle of it. That's the type of thing you want to look for here. So this gives you a way of evaluating how much noise you have in the system, and if your cysts look like clear cysts or if they don't. And that's another thing you want to document with a photograph.
Now, ladies, did you guys recall what a cyst was?
A mass filled with like fluid, I think.
Yeah, good. Okay, okay. I mean, yes, okay. Well, mass more, my dear, mass is okay. It's a correct answer, correct word. But what the word mass mainly or more likely indicate is that okay, it's something which has a form or shape or is more on the solid side. Okay, the cyst mainly is going to be as okay a membrane that contains a fluid. Okay, now ideally speaking, yes, okay, most likely as okay that fluid should be appearing black, which means yes, okay, we'll give you two things. Okay, two clues. First of all, it is a thin fluid. Clear? Okay. And what you don't see is okay, deeper to the cyst is okay, going to be is okay, what we saw earlier over here, shadows. So that may tell you that okay, well, okay, we have a cystic structure, but what it contains is going to be it's okay, a thin and or clear fluid. Okay. Whereas if okay, as you see, yes, okay, the outline of the cyst, but as okay, within the cyst you see some brighter reflections. That may indicate that the fluid within the cyst is of a thicker consistency, or is going to be thicker. And what you most likely as okay will see then is going to be as okay some degree of shadowing. Okay, now that may become important if, for instance, okay, a biopsy needs to be taken from that cyst. Okay, okay, did that make sense? So, and that's okay. The following chapter, when we talk about artifacts, that's okay. Artifacts, that's okay, are going to that's okay be things that we see on the image, but it's okay. It's not always going to be that artifacts are going to be bad. They may even have okay as a diagnostic value themselves, or because that's okay help in the diagnosis. Okay, well, ideally, it's okay. Go. This is all okay. As we can say, it's okay. Clear cysts will be looking like. Okay.
If I go back over here to my frequency, and I was explaining that the transducer with a higher frequency will penetrate less in the body. That's another typical function you might want to measure. So you look at a phantom and you find out the last part where you can actually see the image before it just starts to turn to noise and you can't really see any detail. If I go and I change the frequency of the probe to a higher frequency, I went from a 5 to an 8, and you can see how that dropped off, and my amount of penetration.
You can actually say that, okay, all this here. The reason that you're not going to see this is because of attenuation. That the sound mainly is okay attenuated at, because it's okay at this depth here and beyond. Okay. Mainly as he has okay adjusted the frequency on the system.
Has dropped all the way down to there. That doesn't show a problem with the probe. It shows that we're using a higher frequency transducer. Again, you would document that so you can compare one probe of the same kind and be able to find out if it's performing the way that it should. Those are the most typical uses of an ultrasound phantom, and an ultrasound 2D grayscale phantom like this one, a tissue mimicking phantom, is by far the most common. I told you there are other phantoms, the ones I mentioned before, such as the breast, the prostate, and the head and neck. Those are just similar phantoms with a little different physical structure so that you can put a transducer that would be used for that. But they also have a fetus 3D transducer that looks literally like a fetus embedded in a block of gel like this. And what that's particularly good for is doing a 3D scan where you're doing reconstruction. You want to be able to see a face. That's very difficult to do, and you'd have to have a good phantom in order to pull off something like that. And you'd be able to see that that was 3D. What you'll notice is that we're not doing any color in this phantom. The one thing that a typical phantom like this does not do is it doesn't do Doppler, which would include color Doppler. And that's because that will only work with moving targets and something with roughly the same ultrasound characteristics as blood. And there are very expensive high-end phantoms rather to do that. One of them is called a string phantom, and it literally is a block of water. It has some material inside that is roughly the acoustic properties of blood, and it has a moving string that has small beads on it. And because of that, it can measure the motion, and it can actually verify that you've got the correct frequency scanning for your Doppler, and it will even do color and show that it's got the right frequency. Those are much more uncommon because they're very expensive, and they typically would just be in a good lab that had a reason to test that. Most of the Doppler verification is actually done electronically now, where it can inject a frequency and measure it back. So that's a use you're going to find of your transducer. It's much easier than scanning your body. Your body's a great phantom if you do yourself all of the time and you're very familiar with it, but this has the advantage of being able to document the exact same settings, exact same everything on each system you're looking at, and to be able to track it through time. Use your phantom well, it'll help you out, and it will very easily show you if you've got issues with the system or not. And that's it for a 2-minute tip today.
Okay, ladies, so that was your phantoms. And or yes, okay, what we could call yes, okay. Now just go to page 300 and 386 in your book. Are you guys there?
Yes.
386. And you may see the heading that says dead zone. Is that clear? So what's going to be dead zone? Now zone you can mean says okay, that's going to be okay a type of area. or we can say it's okay, space. Okay. Now that doesn't mean that, okay, yes, this kind of dead, but mainly as okay, just a zone right next to the transducer. So let's say as okay, the reference is okay R. That's okay, this is your transducer. Okay, we can say as okay, we even apply it okay as a thicker thin film of gel. But it's okay when we as okay place that on the skin of the patient's body. Okay. Now, right immediate to the transducer is going to be as okay, this area here. That will be called the dead zone. Is that clear? Okay. So what would that mean? That would mainly mean that okay, as in this dead zone here is okay. Main is okay because first of all, as okay is going to be as okay. Because it's okay at very shallow depths. And what we mean is okay, having the depth zone is going to be as okay that the image is inaccurate. Which mainly would mean that okay, yes, if we for instance okay intend to scan a structure which for instance okay is in the dead zone. Okay. That's why the main is okay to do so. Main is okay just makes a fake dead zone. Mainly is okay by we say it's okay. We take a transducer. We still apply the gel. But what the main is okay will do is okay as they place a bag with fluid, and then you have the skin. Oh, that's. And what we actually did was that this area here, that now is actually is okay represented by as okay, or actually it's okay, this bag filled with a fluid. Usually it's okay, they would just use a bag with regular distilled water. But that's going to be as okay, the area which now will be as okay, your dead zone. And that's how you actually, it's okay, now we'll be able to, it's okay, scan, let's say it's okay, these structures here with a greater accuracy. Is that clear? Did that make sense?
Yes.
Okay. Okay. So here we actually as okay, we can say as okay, we fool the system. Okay. Not fool it, but as okay, we use as okay. We change the as okay, the dead zone. Well, it's still the same. Very shallow depths. Okay. Closer to the transducer. Okay. Okay. Is going to just okay, we mean it's okay, just scanning this bag here with clear fluid. Most likely, as I said, distilled water. Okay. And okay, as an area below the dead zone. Yes, okay, where we mean yes, okay, say that okay, as here the image is going to be more accurate. Will become this right here. Okay. Or you can say, yes, okay, you may use this method here. Yes, okay, if you, for instance, okay, are going to be scanning very superficial structures. Okay, something like, okay, you can say, okay, a subcutaneous cyst or a cutaneous cyst and things like that. Okay, because due to the dead zone, you may not get, okay, yes, an accurate image of, okay, yes, the area of the structure here. Is that clear? Now, ladies, if you guys go to, yes, okay, the 4th paragraph, the one that reads higher frequency transducer have a thinner dead zone, and a lower frequency transducer have a lower frequency transducer. What would that mean? Please mark this paragraph. The 4th paragraph, the one that reads higher frequency transducers. Can you see that? Can you see that?
Yes.
Okay. Please mark that paragraph. It's 2.5 lines. So we can mean says, okay, if you find this, okay, had tube transducer, we can say it's okay. A high frequency transducer, let's say it's okay, 10 megahertz. Versus it's okay, a low frequency transducer, let's just say it's okay, 5 megahertz. What they mainly will say that, okay, yes, that the high frequency transducer is okay, that's going to have, okay, as a thin dead zone. Let's just say it's okay here, there's, for instance, okay, is 1 millimeter. Contra to, yes, okay, your high frequency transducer, which is going to have, okay, as a thick dead zone. Let's just say it's okay, that may be 5 millimeters. Did that make sense?
Yes, it did.
Right, okay, okay. So that's okay, you can say the higher the frequency, the thinner the dead zone. The lower the frequency of the transducer, the thicker the dead zone. Or if you want to write it, no, it's gone because okay, because that's okay that the frequency transducer, or because okay, of the transducer is inversely proportional to the dead zone thickness. Where you mean because that's okay. You for instance, okay, if you had a high frequency transducer, that will have okay as a smaller thickness of that zone, or the thickness of the dead zone was going to be lesser, and vice versa. A low frequency transducer will have a greater thick zone or dead zone thickness. Did you girls get that?
Yes, so the relationship is
Inversely.
inversely, sorry. Yes.
Okay. If you want to do it this way, or you just want to do it this way here. Now please don't come back to me and say, Mike. And okay, it's a couple of months from now. We use a 10 megahertz transducer, for instance. And we got that okay, yes, the dead zone for that is okay as 2.8 millimeters. It's now 1 millimeters as you told us, that's okay. Back in the days. Well, okay, this is just yes, okay. To give you yes, okay, a sense of the relationship. Okay. Or don't come and say, Mike, well, okay, as a 5 megahertz transducer didn't have a that zone thickness of okay 5 millimeters. It's 8.7 millimeters. It is just yes, okay. So you can say it's okay, well, okay. Higher frequency, yes, okay, lesser thickness. Greater, it's okay. Lower frequency, greater thickness. Did that make sense? So whether you want to write it this way or whether you want to, yes, okay, do it, okay, yes. Your arrows up and arrows down, it's up to you. Any questions? Any question, ladies? Okay. That was your chapter 22. Now, when I said that it was going to be done like bim bam boom, here it is. Now, ladies, uh, I can, I will be sending, yes, okay, you can say it's okay, the links for the videos that we saw today. So if you want, yes, okay, play them again. You always, yes, okay, will have the link. Okay. But as I said, yes, okay, whenever, yes, okay, if that is okay, it's your job on, okay, yes, whatever day you may meet up and just say, okay, you don't have patience for the first 1.5 or 2 hours because, okay, we have 5 machines that need to get there. It's okay, tuned up, or it's okay, the quality assurance. Okay. Those images, that's okay, should be saved and not on your phones because you may end up okay going on a vacation if, for instance, okay, your facility and so on, so on, so is getting audited, and they say, okay, where is the yes, okay evaluation of September 11, 2023? Who did that? Well, okay, it was so and so who was due to do that. Well, okay, where is she? Well, okay, she's on vacation right now. Okay, we don't have any proof that it actually is okay was done. Why? Because you had taken your phone with you on your vacation. Okay, and you may be taking okay, it's a crazy selfie in the middle of okay as the ocean, and the next thing you know is broop, you drop the phone down into the Atlantic Ocean. And where goes the quality assurance then? With your phone. Okay, so that's okay. Those images should be saved on the system. Okay, just like okay, as if you are scanning yes, okay, a patient. Okay. And as you might have seen that okay, yes, you will be able to just okay retrieve saved images and so on, so on, so for comparison and contrast. Okay, girls. Now, do any of you have any questions about quality assurance? Any question about that zone? Okay. Now, any questions about the chapters or the quiz?
I have a question
Go ahead, my name.
about the home line. So the home line, when the flow is flowing away from it, it's right to left.
No,
And then right, no?
no. Listen, dear. Let me just do it over here so we can always compare and contrast. So these are your scans. Okay. And mainly it's okay just so that we are not in doubt. If we are not in doubt, it's going to be as okay the same blood vessel. Okay. So it's going to be as okay the same blood vessel that we will be scanning. Let me just erase these. Okay. Now we can say that, okay, yes. Mainly it's okay just to label something because this is the left side of your screen. This is the right side of your screen. This is the left side of your screen. This is the right side of your screen. Did that make sense?
Yes, it did.
Good. Okay. Now, what we physically as okay will say is okay, well, physically as okay, this is where your transducer is, or physically as okay, this is where your transducer is. Okay. Now what we can do is we can steer the angle of your beam like this. And or it's okay, we can steer the angle of the beam like this. Clear. The reason that we don't steer it like this is because it's okay, it would then have made okay as that 90-degree angle between yes, okay, the beam and the direction of the blood flow. So what we have in both of these instances here is okay that this is not a 90-degree angle. Okay, let me just okay, let's make this one a little bit more so. So we can say, okay, this is your box, which may mean, okay, your beam from your transducer is okay, beam up here is being steered in this direction. Whereas down here, it's like in this one here, the beam is being steered in this direction here. Did that make sense?
Yes, it did.
Good. Okay. So this is your beam. This is your beam. Now, what I said about the home line. Okay, now, my dear, when we scan, you're not going to be as okay physically as okay see the home line. This doesn't mean it's going to be something that you have to. Yes, okay, imagine. So the home line is nothing but it's going to be as okay an imaginary line. Okay, now where will we place it over here? Yeah, this is your home line. Where here, in this scan here, is okay, we are being steered the beam this way. This will be as okay, where we'll consider to be the home line. Okay, so the only rule for your home line is that, okay, yes, it will not be, or it should not cross across your beams. So you cannot say, yes, okay, this is going to be the wrong place for your home line. Okay, so on your scan, that's okay. You say, well, okay, imaginary. This is my home line. Imaginary. This is your home line. Did you get that?
Yes.
Good. Now we have our color map. Now, unless and until, yes, okay, the color map is not inverted. We can mean it says, okay, red color, what would that indicate? Positive Doppler shift, right?
Right.
Good. And blue indicates, yes, okay, negative Doppler shift. Now, what we may see in, okay, yes, let's just label this and say, okay, this is A, this is B. Let's say that, okay, yes, in A, our window, yes, okay, was filled up with, let's say it's okay, blue color. That may mean that, okay, yes, in this blood vessel here, it's okay, we have a negative Doppler shift. Did that make sense?
Yes, it did.
Good. Okay, which mainly will mean that, okay, yes, now what are we going to, yes, okay, take as a negative Doppler shift that, okay, yes, the direction of the blood flow is away from the home line. Did you get that?
Yes, I did.
So when it's away from the home line, I mean, it's okay, mean that it came from the left side, flows to the right. So this is going to be, as okay, the direction of your blood flow. If you had, for instance, okay, a negative Doppler shift. We mainly now mean negative or mainly mean that, okay, yes, away from the home line. Did you get that?
Yes, I did.
Good. Okay. Now, I was the same blood vessel. We can mainly say, okay, well, okay, yes, the blood flow is still going to, yes, okay, be in the same direction. But what is it that we are going to get here? Just by us, okay, steering the beam, it will become a positive Doppler shift. Why? Because now we can mean says, okay, because of steering the beam is okay, the placement of the home line is also shifted. So it's okay, now blood flow in the blood vessel is okay, it's a positive Doppler shift, where the positive Doppler shift means, okay, just means towards the home line. It means that, okay, the blood is flowing in a direction towards your home line, which is still left to right.
I have a question.
That's the second. Did that answer your question?
Yes, it did. Thank you.
Good. Okay. So, for instance, let's just say if it had been blue here, or that blue I meant, that you had a negative Doppler shift where, okay, the blood means, okay, just would have been flowing away from your home line, right? It will mean that, okay, it flows from right to left. Or likewise, if let's say it's okay, this one here had been, it's okay, red. That mean, okay, it's a positive Doppler shift. Which means, okay, what I meant, well, okay, towards the home line. Where do you have your home line? Here. So it's okay, still be flowing, it's okay, from right to left. Did that make sense?
Yes, it did. Thank you.
Okay, so that's pretty much okay. That's just what you can say is okay. A way of, let's say, it's okay, predicting. Or we can say, okay, try to determine the direction of the blood flow in the blood vessel that we are scanning. Okay, yes. Esther, do you have a question, Julia?
I think you just said it, but I didn't quite get it all. Are we gonna have to determine like which way the blood flow goes, or will it already be labeled on the diagram?
What do you mean? Will it be already? You can be getting a diagram like this. With any color. Clear? Now, what you mean is, okay, what I have to do is just, okay, compare this color here to your color map. So this is just, okay, the diagram that you have. And I ask you, okay, what's going to be the direction in which the blood flows? Now, what do you see? Oops, sorry, shit. You see red color, right? Right?
Right.
Right.
Good. Okay. Now, what is that going to be as, okay, the next thing is, well, okay, you will say, okay, red in the color map that I have, what does that represent?
They're going
Positive
towards the
Doppler.
transducer.
Let's say it's okay that it represents positive. Clear? What that positive mean? That, okay, as it is flowing towards the home line. Which may mean that, okay, in this instance, yes, okay, it flows like this, which is, okay, it comes from the left side to the right side. Is that clear?
Yes,
Yeah.
it is.
Good.
Yes.
Now, please be watchful, girls, because it's not always going to be that red necessarily as, okay, indicates positive. Just because, okay, you find it above the baseline, that's going to be positive. This red here is okay, may is okay, let's say represent negative. So if that, for instance, okay, is the case, what would this red color indicate then? That, okay, yes, the blood is flowing away from the home line. Where do you have the home line? Well, okay, it's here, but away from the home line. So it's going to just, okay, be from, that flows from right to left.
Quick question.
Yo,
In this instance, for it to be negative and it's going away from the home line, how will we know the red is going to be negative?
because my dear, if for instance, okay, this was your color map. Right? Let's say it's okay like this, and let's say this. What you will see is, okay, because up here is, okay, it will give you, it's okay, it's okay, max velocity. Let's say it's okay, 20 centimeters per second. Right? Okay. And you can say it's okay, that will also be as, okay. Let's say, okay, we have the baseline at, okay, as a 50-50. So down here is going to be as, okay, 20 meters per second as well. Or what you will see here, this will say minus.
Okay.
Did that make sense? Okay. Now, you may look on your Does it say it? Yeah. On your practical sheet, on a color Doppler. Do you guys see color Doppler?
Yeah.
Good. And if you look at the last function, it says color invert. Now actually that's okay. Is going to be as okay. We can say it's okay. A place on that touch screen that says invert. And when you activate that, it's okay. The positive color becomes negative and the negative becomes positive. Or you actually will see that, okay, yes, the negative Doppler shift is going to be okay on the top above the baseline. And the negative or the positive Doppler shift is going to be okay at the or below the baseline. The same is okay even applies for your spectral Doppler. If you go on the spectral Doppler and you can say it's okay between baseline change and Doppler gain, you see spectral invert, right? Okay. And what I mean is, okay, I've done so far, I mean, because it's easier in that way. Then you say, well, okay, this was the baseline. Idea is, okay, what we have about the baseline was going to be as, okay, positive Doppler shift. And below the baseline is going to be as, okay, negative Doppler shift. Right, okay. So if you, for instance, okay, saw a graph, or had a graph, meaning because, okay, you had a positive Doppler shift. That was going to be like this. Or if you had, okay, as a negative Doppler shift. Let's say it's okay, was going to be like this. But what happened when you, for instance, okay, do what we can call is, okay, spectral invert. Now just look at the word as, okay, the meaning invert. Meaning is, okay, just means upside down, inversely proportional, or inversely proportional, upside down, proportional, right? Did that make sense? Okay, so what's going to happen is that, okay, yes, this is your baseline on your spectrum. And we know that, okay, yes, the baseline means, okay, it's a zero Doppler shift. But it's okay if you invert your spectrum. Oops, sorry. The negative Doppler shift is going to be above the baseline, and the positive Doppler shift is going to be below. So that positive Doppler shift that would have been like this on an uninverted spectrum, once it is inverted, it's going to become like this. And the negative Doppler shift, which was okay, it's like this, comes like this. Did that make sense?
Yes, it did.
Right, okay. And some of you are going to say, Mike, what the was the whole point of this? Now, that's something that I'll be bugging you girls with. But yes, okay, when you go on, it's okay, start scanning. What they may like you to do is red is going to be arteries, blue is going to be veins. Clear? Okay. So, yeah. That's where you act yes, okay, will be yes, okay. You can say yes, okay. Having to yes, okay, invert your image. Invert your Doppler shift. Okay, meaning it says okay, positive, yes, okay, becomes negative, and negative becomes positive. Okay. But actually, that's okay. We'll find as okay a little touch function on that touch screen on your as okay on your ultrasound system that says in word. And when that is on, you mainly say yes, okay, the positive is below the baseline, negative is above the baseline. Whereas okay, if it is uninverted, you can say it's okay, that is not inverted, that is not upside down. And when things are not upside down, yes, okay, positive would be on top, negative would be at the bottom. Did you girls get that? Yes, ladies.
Yes.
Okay. So you can mainly says, okay, look at the color. Clear? Compare that color to yes, okay, to your color map. And then you say, okay, yes, home line. And then okay, yes. While positive towards home line was a negative away from home line. And so okay, which side of my screen is it that the home line is? Is it on the right side or left side? Anything else?
I have a question.
Go ahead, my dear.
What do we need to know about pressure and gravitational energy? Because I feel like I don't have a lot on that.
Now, gravitational, not really much about that one. Okay. Just keep in mind, ladies, that okay, yes. What we can say is okay will be as okay, venous flow from your lower part of the body, as okay, below the heart. Mainly as okay, flows against gravity. Okay. It's going to flow against the pull of gravity. Now, as far as okay, yes, pressure is concerned. Okay, okay. You can maybe as okay talk about as okay the pressure gradient, which is going to be as okay from so from high pressures to low pressures. That's mainly that's okay going to be as okay the flow of blood. Okay. Now ideally it's okay what we said about that okay as at any point it's okay the sum of every energy is going to be the same. In accordance to as okay what we called law of conservation of energy. Okay. No, but in this case, yes, okay, they may, yes, okay, just call it as okay, the Bernoulli's principle. Because what this guy Bernoulli's did was mainly, yes, okay, he established the same relationship. But maybe it's okay between, yes, okay, pressure and pressure energy and kinetic energy. Okay. Okay, so pressure energy means okay, just going to be the energy that your blood will use to just okay apply a pressure against the vessel walls. And it's mainly as okay that pressure that we actually is okay measure in terms of blood pressure. But generally, as okay, it will be greater at the beginning of the circulation, at the mean as okay decreases later on. Clear. And that's where you can say we're going to talk about okay, there are viscous laws, frictional laws, and things like that. It's not really lost by main as okay, just that the energy is okay, changes its form. So it's okay, what previously at the beginning of the circulation was pressure energy. it's okay, becomes frictional energy, or you can say, okay, is going to be lost as a result of friction or viscosity loss and things like that. So pressure energy is going to be as okay, the amount of energy that the blood carries in form of pressure, which will mean that, okay, as it pushes up against that's okay, your circulation against the vessel walls. Whereas kinetic energy mainly is okay. Now, practically meant, yes, okay, if you look at the word kinetic, it's going to just okay be pertaining to kind, which is motion. Clear? Very meaning you could say it's okay, the greater kinetic energy an organ or a system or a structure has or uses, the faster is it that it will be moving. Now that faster or slower is going to be as okay speed. Generally, but mainly because in Doppler it was not just a matter of okay saying yes, okay, the blood is moving at a speed of 15 centimeters per second or 200 centimeters per second or something like that. But also the direction. Does it flow this way? Does it flow this way? Or does it flow like that? So that's why we said, okay, as primary, as okay, Doppler was to determine as okay, the speed, how fast or slow. But actually, as okay, what we also wanted is was okay, the direction. Towards or away. You started saying, yes, okay, towards the transducer and away from the transducer. Or actually, it's okay, it came as okay, towards our scan home line or away from the home line. Or towards or away from, yes, okay, your sample window. Okay. So if I, for instance, that's okay, I'm holding a ball in my hand. If I just throw it like this, what is that I do? I transfer less amount of kinetic energy to that ball. And that may mean that, okay, it will be as okay, moving at a slow speed. Whereas if I go like this, all right, okay. Oops, I didn't mean that. I will actually, it's okay, be transferring a lot of kinetic energy onto that ball, and that will actually mean that it will be as okay, it's okay, moving at a faster speed, or actually it's okay, throw it faster. Okay. So gravitational energy, don't really as okay worry that much about that one. Okay. Okay, dear.
Okay, thank you.
No problem. Are you good upon the pressure?
Yeah, I think so.
You think so?
Yeah, I have that the pressure energy is energy that blood will use to put pressure on vessel walls, right?
Yeah. Yeah. Now, what's the relationship between pressure and area?
Directly.
Shaq, are you saying something there?
I was saying, I don't think it's no relationship.
No. It will be power and area, right? Okay. Because then you can say, okay, power will be as okay, that amount of pressure per area or force per area.
So I was wrong. So the pressure, the relationship between pressure and area is what again?
What was pressure? Oops. What was pressure? Now let me ask you guys, is pressure a variable or is it a parameter?
Variable.
A variables?
What kind of variable?
Acoustic variable.
Acoustic.
Acoustic variable. Okay, what are the other acoustic variables?
Then
Distance is one.
Length and
Motion of particles.
It's pressure, distance, and density, right?
so what was pressure? How did we define pressure?
Concentration of force.
Concentration of force per what? Per student in the class or
Per area.
per area? Or area. So what does it? Yes, okay. Area here is going to be a denominator, right? So pressure is going to be inversely proportional to area. Because the concentration of force the amount of force that is being applied on an area. Okay. Now I don't want to just talk off violence, but just think of it. A small amount of pressure or force as I get same amount of force when it says push over a smaller area is going to just be a greater pressure. Whereas if you take the same amount of force over a greater area or distribute over a greater area, it's going to be lesser pressure. So girls, please, yes, okay. I say that's when you have anything like where your equation of something over here, we can say ABC for instance. Now ABC now is it's means calculated by a numerator divided by a denominator. the common concept, ladies, is going to be that, okay, as ABC is going to be, it's okay, directly proportional to the numerator. And ABC is going to be, it's okay, inversely proportional to the denominator. Now, what we just said here was pressure. Pressure here is okay, mainly was okay, was going to be force and area. Clear? We could take another ABC and say it's okay, density. Okay. But okay, here was going to be as okay, mass by volume. But ABC, which was density, was mean as okay, that's going to again be as okay. And we can say that the density is okay, I was going to be directly proportional to mass. Now, mass, ladies and gentlemen, is okay. What many people, as okay, may refer to as weight, which is wrong because scientifically, or as okay, in terms of physics, weight is going to be as okay, the pull of gravity. Right. So mass means that's okay, it's something that we use when we as okay measure solids. But it's going to it's okay be inversely proportional to the volume, which is mainly as okay, something that we mainly as okay. You can say it's like a quantitative measurement of things which are as okay would be liquids or gases. Clear? Where our standard unit for volume was going to be liter. So you can say it's okay, density is okay as is going to be higher as more solid is mixed in okay the same amount of liquid. And or vice versa. So pressure was the amount of force per area. And that's why I say it's okay, unit was okay as a Pascal, or what we also go call is okay, newtons per meter square. Because as far as your area was concerned, it was going to be as okay, any unit of distance being squared. Volume could be liter, or we could also say as okay, a unit of distance being cubed. So pressure energy is mean it's okay going to be okay an amount of force per area. So how much force is it that okay, yes. In this case, it's okay. The blood will be as okay applying onto an area. Now you can say it's okay, the greater kind of pressure energy, more pressure, which means we mean more force over an area. So when you are putting pressure on a thing, what is it that you're doing? Well, in terms of physics, yes, okay, you are transfer energy. Okay. So that measure of energy mean yes, okay, will be, yes, okay, in this case, yes, it will be a force. That's why they say yes, okay, force of gravity. Which is okay, you mean it says okay, it's going to be as okay, a pulling force. Not a pushing, but rather a pulling force that pulls us. Any questions now? So greater pressure energy, lower pressure energy. Yes, Shaq. You want to say something, my dear?
Yeah, but not about that. My question was something else. My question was about another topic.
Okay, go ahead.
About hydrostatic pressure. Can you ask us, because in the book, they gave example of, hold on, we go to it, like 140, and we have to plus it by, I'm talking about it for the stand-up position. So
Okay,
for the
dear,
ankle, it says you're supposed to add 140 plus 100, which equals 240. In the quiz, can you access a different like can the blood pressure be different? Can you access like it will be like 120 for a stand-up position? Are we supposed to add that 120 by 100? I'm asking all jumbled up. I'm sorry.
Okay, listen. Now, I don't know the specific question that you're referring to, but let's say that okay, we are taking a person who is standing. Clear? Okay. I may say that, okay, yes, his blood pressure here. Well, let's say it's okay, 120. Right?
Yes.
Good. Okay. Now, if I ask, what is the measured blood pressure at, let's say it's okay here, we can say it's okay at the ankle. What you will need to get that is, well, okay, as you will take this 120 And you will have just, okay, we can say, okay, at the hydrostatic pressure of the angle, which was 100. And you will get, let's say, it's okay, 220. Did that make sense?
Yes.
Okay. Now, the same scenario can also be that I say, well, okay, listen, ladies. You can say, okay, the measured blood pressure at the ankle is, let's say it's okay, 250. That's the blood pressure that we measure here. But I'm only asking, okay, yes, what is the actual blood pressure of the patient? Now, for that, yes, okay, you may, yes, okay, we'll say that actual blood pressure, mainly because, okay, at the angle, yes, okay, we had 250. From that, yes, okay, mean is okay, we'll have to, yes, okay, subtract the 100. Okay,
Okay.
which was his hydrostatic pressure, sorry. And okay, what you actually get is, okay, this fellow here is doomed because his blood pressure measures to 150. Which will mainly mean that, okay, had we measured his blood pressure up here, is okay, it would have been 150. This extra 100 here is mainly as okay due to as okay a fixed value of the hydrostatic pressure. Okay, now please, 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 clear your mind goes that okay at the hydrostatic pressure is okay only applies if the patient is standing up. Because okay, if he or she was lying down, there's going to be as okay no increase in the blood pressure at any point, because what the hydrostatic pressure means is okay was okay is increase in the pressure due to the weight of the column of blood. Did that make sense?
Yes, it did.
Okay, so mainly at this point is okay, well, okay, there's no increase in pressure between this and this, this and this, this and this. So whatever blood pressure was measured here is going to be the same if we had measured it here or here or here. Because okay, when the patient is lying down, where he's lying with his looking towards the roof, which is going to be supine, or if he's lying prone, which means okay, lying on his stomach, facing downwards. Okay, at the level of the heart is okay as at the same level as any other area of the body. So that would be as okay, no hydrostatic pressure. So in that case, that's okay. The blood pressure that you have measured, for instance, okay, at his ankle was also going to be 120 if it was 120 here. Did that make sense? Did that make sense?
Yeah.
Okay. Anybody have any other questions?
Can we go over crosstalk? The the mirroring
Crosstalk?
yeah.
No problem, dear. If you want to talk crosstalk, we can crosstalk. Listen. Now, primarily, it's okay, what was it a crosstalk was? Now, as I say, it's okay, we'll come across that again. It's okay in chapter 21, where we mean it's okay, we'll just call it image. It's okay, mirror imaging. Okay, we may say it's okay, call crosstalk mirror imaging in color Doppler. Now, the mention here is okay here in spectral Doppler. And let's say it's okay. Let's say that okay, we have a positive Doppler shift. So that's going to be as okay, the actual is okay Doppler shift that we may be measuring. Okay. Maybe may says okay that this positive Doppler shift, or we have a positive Doppler shift, is the actual Doppler shift that we measure. Did that make sense? So
Yes,
in this
okay.
case, it's okay, he or she will be as okay the real Doppler shift. But what we may see on a spectral Doppler, now they're going to use a different color. Don't say, Mike, why doesn't my crosstalk show up in a different color? It's just, by you mean it's okay, we'll have it going to be as okay, you can see it's okay, true copy. Of your positive Doppler shift, which was real, going to is okay appear on the, in this case, it's okay, the negative side there. So this negative is okay, Doppler shift recording here is fake, it's an artifact. And in this case, it's okay, we call this artifact here crosstalk. Is that clear?
Yes.
Good. Now let's say that okay, yes, if we that have had okay as a negative Doppler shift. This fellow here is okay, is real. Then your crosstalk or is okay, or going to be as okay, this fake positive Doppler shift. It's me as okay, just going to be as okay, and sorry, a mirror image of okay the recording that you see down here. Okay, but mainly will say as okay, when this here has its peak, this will have its peak. Okay, and so and so. Okay, now on a spectral Doppler, okay, because you may see as okay a graph on the positive side, you may see as okay a similar graph just in opposite direction on the negative side. Clear? Right there?
Right, yes, yes.
Okay, and you may be wondering because is the positive the real and the negative the fake? Or is it the positive that is the fake one and okay, the negative that is the real one? Now, my dear, on a spectral Doppler, the one that okay is between these two reflections here is going to appear brighter is real. And the one that's going to appear darker is the fake one. So when you look at a positive and a negative, Doppler shift vary, which I mean is true copies of one another, which means makes what we call crosstalk. Okay, but to determine which of these two here is the real one and which one is the fake one, you mean we have to compare this against this. And if you see, well, yes, the graph of your positive Doppler shift appears brighter than the that the graph of your negative Doppler shift. You say, since this one here is brighter, he is the right one. And since this one here appears slightly darker, that makes him the fake one. So you can say, well, yes, we have a positive Doppler shift. And this fellow here is just yes, crosstalk. Or what we as in regular diagnostic imaging, we call as mirror imaging. And that's what we also call it in color Doppler. Is that clear?
Yes, it is.
Okay.
I have another question.
Go ahead.
Just to verify. Spectral broadening is it also known as turbulence flow, or is it equal to turbulence flow?
No, listen, my dear. Ideally, or most likely, as if you see what we call as spectral broadening. Yeah. Okay. Now let's just compare that to as to a normal spectral Doppler. Now normally says your spectral Doppler should appear something like this. Here. Okay, where you mean you see as the outline of as of your spectrum of your graph is thin. And what we also have is as these areas here, for instance. That what we call as the spectral window. And the spectral windows are clear. Right. Okay. Did that make sense?
Yes.
Okay. So, but just keep in mind, my dear, that as whatever you see here as white is going to be black on the spectrum, and whatever you see here as white is going to be, or whatever you see black is going to be white on your spectral Doppler. Okay?
Yeah.
Good. Now the very same as applies to your spectral broadening. Whatever you see black, here is going to be white, and whatever you see white is going to be black.
Okay, got it.
Good. Okay. But what are we spectral broadening? Well, we can mean it says that first of all, is the thickness, or we can say the outline of your graph is going to be thick. So that means that's just tells us as spectral broadening. But what we also will see in spectral broadening is that as because these were our spectral windows. What is it that they are going to be? Yes, the spectral windows are going to be as appearing foggy. Or maybe that's contaminated by noise. And what is that is noise is going to look like is a lot of small white sparks.
Okay.
Okay, or dots. So mainly as we'll say that in this case, yes, your spectral window is going to be having are going to be filled up with, okay, what looks like, okay, there's a lot of snowflakes. Now, on a spectral analysis, if you call it, what is it a spectral Doppler or spectral broadening will indicate? It mainly is okay. Normally, that's okay. It will indicate that you have, okay, it's a turbulent flow. Did that make sense?
Yeah, yes, it did now.
Okay. The turbulent flow mainly as okay indicates, okay, turbulent flow. There's something as okay in the patient which is abnormal. Most likely, when you have a turbulent flow, that abnormality is going to just okay be stenosis. Did that make sense?
Yes, it did.
Clear? But then again, please, 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 please. It's not always going to be as okay that you say as okay just because we had spectral broadening. Or something that looks like spectral broadening that is automatically going to mean that we have a turbulent flow. Because of those four imposters of spectral broadening. Right?
Right.
Where we say is okay, poor angle. Right, okay. If you have a poor angle, an angle that is close to 90 degree, may as okay produce a spectral reading that's going to just okay be looking like a spectral broadening, but it's not due to turbulence. It's just because we have a poor angle. So what you may do is okay, yes, check on your angle. And as you correct it, you'll see as okay that is broadening back. Spectral broadening may is okay. It's okay. Get less or that's okay, get improved. Which mainly meant that okay, you didn't have okay as what looked like spectral broadening due to turbulence, but it was actually just because of a poor angle. We also said okay, as if your sample window, for instance, okay, was too close to the vessel wall. Could lead to as okay, what will look like spectral broadening, but was not due to turbulence, but means it's okay because of your sample window, yes, okay, B. You can say okay, illy placed. Too close to the vessel wall. Where we can say, okay, the sample window is okay, is too big. You might see something that looks like spectral broadening, which is not due to a turbulent flow. But mainly because, okay, you have chosen, as okay, you set your sample window, which was too big. Did that make sense?
Yes, it did.
Okay. So that's okay, those four imposters of spectral broadening, which means what I mean. Well, okay, is you see something that looks like spectral broadening that you may think is due to yes, okay, turbulence, but it's not. I mean, it's okay just because of some poor settings on your behalf. So you get okay, fix those. You may get okay, so get rid of what looked like a turbulent flow, which wasn't due to a turbulent flow, but actually it's okay. You is okay. had to, yes, okay, or needed to, yes, okay, adjust your settings. Did that make any sense?
Yes.
Okay. So doing Doppler, girls, or not just Doppler, any kind of ultrasound is, that's okay, just like driving a car. So you adjust things according to, yes, okay, you can say it's okay, the flow of traffic and things like that, right? Okay. Let's say that, okay, you were flying down the highway at a speed of 75 miles per hour. Okay, that may be okay as long as
Traffic. Yeah.
no traffic, right? But if you go into, it's okay, if you get into a traffic jam, that's okay, take an exit off the highway, yes, okay. You may like to, yes, okay, reduce your speed, right? Because you may get a speeding ticket. So that's okay. When you see something, that's okay, you do something. And what to do and what not to do, yes, okay, that was mainly, yes, okay, what this whole physics thing here was about. Because then you also have to think of, okay, as the positive consequences, and you can say it's okay, negative consequences of the actions that you take. Did that make sense?
Yeah.
Good. Any other questions?
Can we go over power Doppler?
Power Doppler. No, my dear. Now, if you just break the word down into two things, right? We can say, okay, Doppler mainly as okay, we'll refer to, we can say, okay, measuring. And I mean, yes, okay, going to, yes, okay, use the word speed of blood. And the reason that I use the word speed here is because in power Doppler, okay, there's no direction. Did that make sense?
Yes.
Now, since there is no direction, that's why they also, it's okay, call it, it's okay, the non-directional Doppler. There he says, okay, when there's no direction, that may mean that there's going to be no positive Doppler shift. And okay, likewise, no negative Doppler shift. There, okay, so when we look at the other word, which is power. Okay. Well, okay, as back, we say as okay, power was okay at the rate of transfer of energy. But it can mean says okay, this power here actually is okay, just will measure the amount of energy. Practically speaking, yes, okay, what it will do here is it's going to, yes, okay, measure your kinetic energy, which will give you, yes, okay, yeah, greater speed if you had more kinetic energy. Or it may give you, yes, okay, a lower speed if you had lower kinetic energy. Did that make sense? And how is it that, okay, it's going to just, okay, display these Doppler readings here of your speeds? It's still just, okay, by color. So it's okay, you will still have just, okay, your blood vessels filled up with a color. And this color here means, okay, just means that, okay, as there's blood flowing at a certain speed, no direction. Did that make sense? And the major point that you guys will have to remember about is, okay, it being no direction, having no direction. It's a no positive, no double shift, no negative is that there will be, yes, okay, no aliasing. So that's okay, that's, we can say, okay, we can say one of the advantages. Okay. Which means yes, okay, will also yes, okay, be used in case that, okay, yes, you want to, yes, okay, measure high velocities and or yes, okay, low velocities. The positive part of, okay, yes, being able to, yes, okay, measure high velocities is, okay, those high velocities will not give you aliasing, it will just tell you, okay, blood is flowing. The low velocities mainly because, okay, this here has an increased sensitivity, which means, okay, makes it more likely to, yes, okay, be able to, yes, okay, detect or even, yes, okay, record low velocities. Is that clear? Which are low velocities, sorry, low speeds. Means, okay, because it's have a low increase high sensitivity, so it will be able to just, okay, detect small amounts of kinetic energy. But because it is non-directional, you will be able to, okay, record yes, okay, higher amount of kinetic energy without aliasing. So the main purpose of, you can say, is, okay, power Doppler is mainly is, okay, just to, so okay, let's ensure, let's determine, is there, okay, as a good blood flow here. Right. For instance, okay, you want to check on, yes, okay, what they call perfusion of an organ. Is it receiving the amount of blood that it needs? Okay. You're not really interested in, okay, how fast or slow the blood flows. Your main goal is, well, okay, I would like to like check on, okay, does this tissue or this organ here receives any blood at all? It may not be a lot, but at least, okay, we can say, okay, something is better than nothing. Any questions? Okay. I mean, that's okay because it still, yes, okay, shows up. I mean, that's okay, still is going to, yes, okay, display your Doppler by filling the vessel up with a color. That's why it's okay, they call it, it's okay, a color angio. Yeah, we also call it, yes, okay, a energy mode. Mainly because it's okay, it just measures the amount of energy. Which energy? Kinetic energy. Because kinetic energy means is going to, it's okay, be. In this case, it's okay, not velocity, but actually it's okay, just speed. Okay. Any other questions? Yes, girls.
From chapter 18, the Reynolds number or Reynolds number, like, does it predict the flow?
Well, you can mainly say it's okay if you have a Reynolds number which is less than 1500. You can say, well, okay, as you have a laminar flow.
Okay.
A Reynolds number greater than 2000. Yes, okay. You can say it's okay. Predicts, I mean, it's okay, will indicate that you have a turbulent flow. So
Okay.
that's all that you need to know about that one.
All right.
Clear? Okay. And some of you say, well, okay, then what about it's okay between 1500 and 2000? Well, that's the gray zone.
Right.
Right. Okay.
All right. Thank you.
No problem there. So all about it's okay, your Reynolds number that you need to know is okay as what Reynolds number is okay will indicate a laminar flow versus turbulent flow. So up to 1500, 1500 was a laminar flow. 2000 and above was turbulent flow.
Okay. Thank you.
No problem. Yes, girls. Anybody else?
The question's not from the book, but I just, tomorrow when we have our pictures to go on for our test, is it gonna be in color so we know? Like, is
If
our quiz
color
gonna be?
color is going to be relevant for you to just okay determine it, yes, of course.
Okay,
Because that's okay if I ask, okay, what's the direction of the flow? Because blue is going to be gray, red is going to be gray, and that will be yes, okay. I may be considered a cruel person, but I may not be that cruel. So okay, you should have been able to just okay then compare okay the shades of gray here. Okay. So if it's a question that's okay where you need the colors to just okay determine what's being asked, of course, it will be colorful.
Can we go over briefly the home line? I just
Home line?
wanted to make, yeah, I just want to just go over real
Okay, my
quick.
dear, listen. First of all, when we turn on the machine, don't ask me, Mike, where's the home line? I don't see the home line. It's an imaginary line. Clear? So when I say it's an imaginary line, that's going to be a line that you will draw in your head. So, okay, well, this is my picture. This is where my home line goes. Clear? So this was your blood vessel. And we may say that, okay, this is our box of, yes, okay, steering, a steering of a box. Now, ladies, what I told you was the home line will be here. So this is pretty much okay. We'll say, okay, yes, if my box is steered like this, this will be my home line.
Okay, and that would tell you it's going from right to left.
All upon, no, okay, then you can say, well, okay, because we can say, okay, this is the left side of your screen. This is the right side of your screen. Mainly because, why do we call this one the left and this one here the right? Because this is on the left-hand side. On the side that you have your left hand. When you look at the screen. Why do we call this one here the right side? Because that's the side of the screen on the right-hand side. Right-hand side of who? Of you. Did that make sense?
Yes.
Okay. So mainly as okay, that's going to yes, okay, to yes, okay. Enable your chance, yes, okay, what the question is. It's going to flow from right to left or left to right. Now, for instance, okay. Did we have the color map? For instance, okay, that was here. Let's say that this is your color map. Where we may say that, okay, as yellow, for instance, okay, indicates positive and red is, okay, in this case, here it is. Sorry. Negative. Now, for instance, okay, if your blood in the blood vessel here was, yes, okay, or your vessel was filled up with yellow, that yellow color is okay, and according to your color map indicates a positive Doppler shift, right? That positive Doppler shift mainly will mean that, okay, yes, the blood is flowing towards the home line. Which may mean that, okay, they come from the right side and flows towards the left. So you can mean it says, okay, that the blood flows from right to left. Did that make sense?
Yes.
Good. Whereas, let's say it's okay, at this blood vessel here, it's okay, shown red. Now, in accordance to your red, according to your color map here, yes, okay, what is the red indicates? Yes, okay, marks. It marks a negative Doppler shift, which mainly mean that, okay, yes, the flow of your blood in this blood vessel here is in a direction away from the home line, which mainly mean that, okay, yes, it came from left, but it's flowing in a direction away from the home line, which is going to be right. Did that make sense?
Yes.
Good. Now, okay. Now, ladies, let's just do, that's okay, the unthinkable. Why unthinkable? That's okay. Let's say that, okay, as our box was steered like this. Now, in this instance, yes, okay, this is going to be our home line. Did that make sense? Did that make sense?
Yes.
Good. Now, my dear, if your friends, yes, okay, saw that, okay, yes, the blood was filled with yellow. Now, yellow was a positive Doppler shift. And what the positive Doppler shift mean? Towards the home line. So it flow like this, or which way is okay, mean that it flows from left to right. Whereas, if our beam was steered like this, the light blue, but we see the blood is okay, is indicated or marked by okay as a red color, which is negative. That may mean that okay, the blood is flowing in a direction away from the home line, which may mean it flows this way. Which may mean that okay, it comes from the right, but it flows to the left. So it means okay, it goes from right to left. If that makes sense.
Yes.
Right, okay. Now you mainly can say, well, okay, yes, it was the same blood vessel. But let's say it's okay, the same flows, or the flow in the same direction. But just because, okay, we have steered the beam from this to this, the blood vessel goes from as okay, having a positive Doppler shift to a negative Doppler shift. But the direction of the blood flow in the blood vessel is still the same. You got that?
Yes.
Okay. Anything else?
I have a question. How do you fix the the image that you showed us would look like it was bleeding into the vessel was like bleeding into the thingy?
You're talking about ghosting?
Yeah.
Wall filter.
Okay.
Okay. Because, okay, what was it a ghosting on a color Doppler versus cluttering on a spectral Doppler was? Mainly it's okay, just recordings of very, very low Doppler shift frequencies. So what the wall filter mainly did, my dear, wall filter does it eliminates, because it's okay, very, very, very low Doppler shift frequencies. Right, okay. Did that make sense?
Yes.
So on a spectral Doppler, my dear, where is it that we have these very, very low Doppler shift frequencies? Are going to, yes, okay, be adjacent to your zero Doppler. Because if you start from zero and start, that's okay, doing accounting, first you go with the small numbers and then you go bigger and bigger and bigger, right?
Right.
Okay. So on a spectral Doppler, okay, as you turn on the wall filter, and maybe that's okay, increase your wall filter, you actually, that's okay, on the spectrum, actually, that's okay, we'll see a little, most likely, that's okay, light greenish bracket. That's fine. Here's us getting SOK bigger and bigger. By SOK only to SOK a certain extent. Okay. So it pretty much okay as does the same as reject. Where reject means is okay only as okay eliminated low intensity signals. I can put it this way. Which means okay what we call noise. Okay, but doesn't eliminate the high intensity signals. So the same as what the wall filter does. It only has okay, eliminates the low density or low intensity or low Doppler shift frequencies, but leaves okay the strong Doppler shift or yes, okay, great Doppler shift frequencies intact. Right, okay. And in the blood vessel, where is it that you see it's okay, low frequencies or low Doppler shifts? In a vessel, where do we have low Doppler shifts? which we can mean is okay, it will be as okay. Due to low velocity. By the vessel wall. And it's pretty much okay as this, actually as okay, looking as okay as it is leaking out. On a spectral Doppler, okay, these will have shown like okay as small as okay, waves between the big spectral Doppler readings. So what may happen as you apply a color filter here is okay as it may get rid of this and this, but if you keep on increasing, it may also cause as sorry. You can say okay, slide. It's okay, decrease filling of the blood vessel. Where you actually is okay, may get this. And where you may see okay, the peripheral of the blood vessel actually is okay, also is okay, may show zero Doppler shifts. While the blood vessel actually becomes less and less filled. Is that clear?
Yes.
Right, okay. But. We can say it's okay. This being less filled of a blood vessel is also okay. What you may see is okay in case that you increase the scale, which we just call as okay, increasing the PRF. Okay, but the main thing is okay as what happens with the wall filter. Oh, let's put it this way. What is it that you may get by increasing the wall filter? Sorry, increasing the scale that you don't get with the wall filter is by increasing the scale is okay. You also is okay get rid of eliasing. Your increasing of the wall filter is not getting rid of eliasing. So this blood vessel is okay showed that says okay both ghosting. And you might even yes okay says okay have some that says okay eliasing. If you apply the wall filter will only as okay get rid of the ghosting. Clear? But you will still have the eliasing. Did that make sense?
Yes, it did.
Right, okay. Whereas if you, for instance, okay, increase the scale. If you increase the scale, that's okay, increase your PRF, it will get rid of both the ghosting, because what was it the ghosting was? Low Doppler shift frequencies. But it will also get rid of the eliasing. Did that make sense?
Yeah.
Is that mainly because okay, increasing the scale mainly cause it as okay, it is going to just okay cause a reduced sensitivity. Well, reduced sensitivity mean that okay, we'll not be able to just okay register the low Doppler shift frequencies due to low velocities. Which in this case has okay produced as okay this artifact that we call ghosting. On a spectral Doppler, those low Doppler shift frequencies were what we call, okay, sorry, cluttering. So it's the same thing, just going under two different names, whether you talk about it in color Doppler versus spectral Doppler.
I have a
Okay.
question.
Okay, Dr. King, did I answer your question there?
Yes, you did. Thank you.
Okay. Yes. Yeah, go ahead, Maria.
Do we need to know what the speed of blood is?
Because that's going to vary.
Okay, thank you.
It's going to vary. You can say it's okay in an artery versus vein, right? Right?
Right.
Good. So that's something that you will be bothered about. Okay, have to be bothering about once you do start your actual vasculars or vascular scanning. And then you will come across and actually see that, okay, a normal speed of different blood vessels are just, okay, different arteries will be different. Now, okay, as would it be much to know what the speed of this artery is versus this? That's something I will leave for your scanning model teacher to deal with. Okay. But yes, there will be as okay velocities of blood vessels that you may have to remember, because you may see, okay, shoot, here is okay, it's more than the normal. It's less than the normal, then okay, as what should be the bell that should be ringing, right? But right now, yes, okay, I'm not going to be bothering you guys with that. Anything else? Can I ask a question?
Sure.
Okay. Why is it that only has been King, Dr. Brown, and Geraldo who have been asking questions? Okay, those of you who didn't ask a question, then it will mean that, okay, yes, you are expected to get 100% tomorrow. Okay, the three girls who have been asking questions, they're still alive, right?
Yeah, we're alive.
I am.
Yeah.
Okay, I haven't even verbally killed you yet, right? Okay, good. So those of you who haven't asked a question, okay. Do you guys want a short break from looking at me? Take a breather, okay, ladies? Breathe and read. And I'll see you ladies back around 12 o'clock. Doppler shift equation. No, they cannot be all related to one another. But you can mainly say, look, now when you say the Doppler shift is equal to 2, you can say, okay, multiply by, okay, velocity of blood. Multiply by, is okay, the transducer's frequency. Multiply by, okay, the cosine theta value of an angle between direction of blood flow and the beam. Clear? Now, this cannot be directly proportional to this, cannot be directly proportional to this. But what we can say with surety is that your Doppler shift is going to just, okay, be directly proportional to, if we say this one here is B, this one here is B and C, that is going to be directly proportional to A. It is also going to be directly proportional to B, and it's also going to be directly proportional to C. Did that make sense?
Yeah.
Right, okay. Let's just take an example. Let's say that, okay, we have a blood vessel in which, for instance, okay, we have a low velocity. And let's just say that, okay, as we scan it, let's say it's okay at a 0-degree angle, which has, okay, like a cosine value of 1. Clear? Now, if in this case, yes, okay, now if you see 1 and 2, let's just give us, okay, let's take 2 different colors. Let's see. 1 and 2. Now, if you say that, okay, 1 is going to be, okay, if we had, for instance, okay, high frequency, that will cause the Doppler shift to be high. Okay, because let's say it's okay, we say, okay, it was 10 megahertz. Where, okay, the same blood vessel at the same angle and same everything, but it's okay, measured with a low frequency transducer. Let's just say it's okay, 5 megahertz. It's going to give us a low Doppler shift. Did that make sense? So what caused us to get a high and low Doppler shift in this case here was because we used a high frequency or a low frequency transducer. Did you get that, my dear?
So everything is related, directly related to the Doppler shift, but the other ones are inversely related to each other?
No.
Oh.
They will still be directly related because now we can say, if you, for instance, okay, keep the frequency of the transducer, we say B, well, okay, so let's choose B here as like this. And say, well, okay, yes, 5 megahertz. But now if, for instance, okay, change the velocity, let's say it's okay, there is 2 different vessels that we are measuring, but using the same transducer. In one blood vessel, it's okay, we say 1. That may be, it's okay, a great speed. Well, okay, in the other instance, we can say it's okay, vessel 2. It will be a low speed. Let's say that's okay, that gauge speed was 100 centimeters per second. Where, okay, as in the blood vessel where we actually record a low speed. Well, let's say it's okay, just 20 centimeters per second. Well, we are Doppler shifts here. Now the blood vessel where the blood was, that's okay, when we record where the blood was flowing at a great speed. Well, okay, yes, we will have a great Doppler shift, right? Whereas, okay, as if we recorded the velocity, that's okay, if we talk, that's okay, of the Doppler shift in the low velocity blood vessel, well, okay, our Doppler shift will be low. Did that make sense?
Yeah.
Clear? Where you can then say, well, okay, yes, what if we were measuring the blood vessels, okay, speed of blood in a blood vessel where the speed was flowing at a high speed using a high frequency transducer. In that instance, okay, your Doppler shift would be very high. Did that make sense?
Yeah.
Okay. But individually, all these three, whether it was the velocity of blood, is going to be directly proportional to your Doppler shift. The frequencies transducer, or the frequency of the transducer, sorry, is going to be directly proportional to your Doppler shift. And the cosine value of the angle is going to be as okay directly proportional. Where we know that okay as far as okay as our cosine theta values of the angles we have, highest is for 0-degree angle and 180-degree angle, which highest okay cosine theta value was 1. But on the other hand, we can say as okay, the lowest value, a cosine theta value of angles was going to be as okay for a 90-degree angle, which was 0. Did that make sense? Where we made is okay, based on this can say that okay, yes, that it's at an angle of 0 degrees and 180 degrees. That the measured velocity is equal to the actual velocity. Clear? There, if we find this, okay, scan, okay, let me just go to another slide there. There's if we go, yes, okay, so it says, okay, 0 and 180 degrees is okay. Their cosine value was 1. We can then say it's okay, angles such as 60 degrees which is going to be, okay, give us a positive Doppler shift. And 120 degrees is going to be, okay, the negative Doppler shift. Or, okay, they had, okay, it's a cosine theta value of 0.5. Here. So at these angles here, we can actually say, okay, that the measure velocity is going to be equal to actual velocity multiplied by, okay, as the cosine theta value. So mainly it's okay when we compare, let's see, it's okay, this one here versus this one. This is a lower cosine theta value. So in this case, as okay, we can mean it says okay that we have a lower measure velocity, or it's okay a lower Doppler shift. Contra to this one here. I mean, because of a greater cosine theta value, we will have, okay, it's a greater Doppler shift. Or we actually say that this Doppler shift actually is going to be, okay, equal to the actual velocity. Yeah. Where we went to, let's say, is okay, if we says, okay, what about the angles like 30 degrees and 120 degrees? But okay, they had a cosine theta value that was greater than that of 60 and 120. Just keep in mind that this was going to be positive, this was going to be negative. Right? Clear? Now the cosine theta value of these two angles here was 0.85. Where you mainly will say, well, okay, comparing it to, yes, okay, 60 and 100, not 60, sorry, 150, sorry. Comparing to, yes, okay, 60 and 120. Okay, here is, okay, where we mainly says, okay, that the measure velocity, or yes, okay, Doppler shift is greater than the Doppler shift here, because of the greater cosine theta value. Or we can say, okay, more closer to the actual velocity than at a 60-degree angle. Did that make sense?
Yeah.
Any questions?
Yes, I have one more question.
Okay, go ahead, my dear.
It's in the book on page 525.
Ooh, okay, checking me very far. 525.
25.
Okay, good. That's fine. So page 525. See?
Question 498. I didn't get that one.
498. Good. Now, let's see if we can read this question together. Now, blood is moving at a velocity of 2 meters per second. Good. So we can say, okay, our velocity is 2 meters per second, right?
Yeah.
Good. Now it creates a Doppler shift of 300 hertz or 3000 hertz. So the Doppler shift that we get is 3000 hertz. Clear?
Yeah.
Good. What would be the Doppler shift if the velocity increases to 4 meters per second? So if you increase the velocity of blood from 2 meters per second to 4 meters per second, then maybe it's okay, just ask us where is going to be, it's okay, your new Doppler shift. Now, my dear, it's very straightforward. Because like, they mainly was assumed that, okay, everything else is the same.
Yeah.
The only thing that you happened was to say, oops, while scanning the patient, and all this, okay, he goes into tachycardia or something. And okay, the blood starts flowing at a greater speed. And what you mainly can see is, okay, what was the change in the speed? It actually is, okay, it just doubled. Okay, I hope everybody will be able to see that, okay, 2 times 2 becomes 4, right?
Right.
So the speed doubled. So what's going to happen to your Doppler shift if they are directly proportional? Well, okay, it's just going to double as well. So it goes to, yes, okay, 6,000 hertz. Because what was it we just said? That Doppler shift is directly proportional to velocity of blood. Did that make sense?
Yeah.
So first we started at, yes, okay, we can say it's okay, at a low velocity, which was 2 meters per second. We doubled that to get, okay, as a velocity of 4 meters per second. But to begin with, yes, okay, that 2 meters per second, yes, okay, just gave us a Doppler shift of just 3000 hertz. But say, yes, okay, the velocity increase, what's going to happen to the, doubled? Well, okay, most likely we'll say, okay, the same will happen to the frequency of our Doppler shift. That's also going to double from 3000 to 6,000. Did that make sense?
Yes.
Good. Now, if you went in opposite direction and say, okay, as the Doppler shift was 3000 at a 4 millimeters or 4 meters per second velocity, right? Okay. But then, yes, okay, it became, this Doppler shift went from 3,000 to, let's say, yes, okay, 1,500. What most likely is, okay, what happened to the speed? Then you can say, well, okay, here it just became half. So most likely is, okay, your speed will also have come from, that's okay, 4 meters per second to back to 2 meters per second. Because we had a fall in the, or we had a decrease in the Doppler shift to half. We can say, as okay, most likely as okay, the speed of blood has halved. Or maybe as okay, if they talk frequency of the transducer, that frequency would have halved to cause the Doppler shift to half.
Okay.
Did that make sense?
Yeah.
Or you can even say as okay, at a high Doppler shift, as okay, we were scanning at a 0-degree angle or 180-degree angle. We might have gone from a 0-degree angle or 180-degree angle to 0 to 60 degree and 180 to 120 degrees, because what is that these has? These had a cosine value of 1. These two had a cosine at a value of 0.5, but they're most likely not going to go into that.
Okay.
Did you get that, my dear? Okay. But just remember, yes, okay, we can take the same and say, okay, yes. Let's say it's okay, let's say that, okay, we have a Doppler shift of 3,000 hertz. Clear? By a transducer, let's say it's okay, that a transducer frequency, you can put anything, okay, was 10 megahertz. Clear? Okay. Now they may say, okay, what if we, yes, okay, reduce the frequency of the transducer from 10 megahertz to, let's say, it's okay, 2 megahertz. That's going to be too much math for you guys. That's fine. Just take it down to 5. That's okay. And then ask you, okay, what's going to be, okay, the Doppler shift here. Now, please keep in mind, okay, if they say Doppler shift, that's when you say it's okay because the velocity, the frequency is reduced to half. So is the Doppler shift also going to, it's okay, reduced to half from 3,000 to 1,500 hertz. Did that make sense?
Yes.
Good. Now, please, 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 please. If they ask, yes, okay, well, okay, this was your transducer's frequency. This was your Doppler shift. Well, what's going to happen to the velocity? If you, yes, okay, reduce your frequency of the transducer. Now, ladies, the velocity here is going to remain the same. Velocity of blood. Now, the reason that you make it, yes, okay, a lower Doppler shift by reducing the frequency is because you reduce the frequency. That's going to cause, okay, you can say, it's okay, the Doppler shift here is okay, will be half of 3,000, which is going to say, okay, be 1,500 watts. But in both instances, okay, whether you use the high frequency transducer or your low frequency transducer, the velocity might have been the same. Because it says, okay, 200 centimeters per second. Did that make sense?
Yes, okay.
Okay. So that's okay, be watchful.
Okay.
Anybody else? Nobody?
I have a question.
Okay, please.
So bidirectional flow is just a synonym of flow reversal, right? Or are they different things?
No, that's more of an audible thing. Just think of your sound system. Because that's okay, what you actually is okay, may start, yes, okay. When you hear the Doppler shift, it may sound strange, but okay, it's your ultrasound machine actually, it's okay, it's okay, also equipped with speakers. So whenever you turn on the Doppler shift and start, it's okay, measuring the blood flow, you will hear something like that. Okay.
So what's the difference between both?
Pardon me?
What's the difference between them?
Between what?
Bidirectional flow and flow reversal.
Now, flow reversal, well, okay, you say it's okay, you primarily have a positive Doppler shift. And let's say it's okay with a negative Doppler shift as a flow reversal. Okay. And you can mainly say, it's okay, the speaker that will tell you positive Doppler shift may be loud versus the other one will be low. But flow reversal is just okay as if you have been to a movie which have that okay as not just 3D, but actually as okay, the sound system. They mainly see as okay, a plane, for instance, okay, approaching from this side of the screen. You actually also hear the sound from this side. Yeah, it goes like okay, and you then hear the vehicle sound on this speaker here. Did that make sense?
Yeah.
Just as you as okay, it's okay. They may say, okay, you are standing on a street or whatsoever. You see a motorbike or a car or a truck or something is okay approaching you from this side. Now, if you have normal hearing, yes, okay, you mainly hear, okay, the loud truck on this side by this ear. And that will register that you actually look this way. Did that make sense? Yeah, okay, when it goes like this, and then okay, leave. You may as okay with that here is okay. The sound is okay on this ear more, and okay, but it just becomes dimmer and dimmer. Whereas flow reversal, my idea is mainly is okay, that like that. What you mean, he says, okay, we have positive flow, then slight negative, positive, then slight negative, positive, then negative. Did that make sense?
So could it be explained as like side to side and front to back, or no?
No, not really, Maria. Just put it this way, my dear, flow reversal. When you're driving ahead, this is your normal direction. When you go like this, that coming backwards is flow reversal. And that's what normally, there's nothing wrong about it. That's going to be something that normally happens during diastole. Did that make sense?
Yeah.
Good. Now, you can say good is good, but then too much good is bad. So you have too much flow reversal in your blood vessel. What may that indicate? What we call, yes, okay, most likely is okay, an aortic regurg.
Wait, what did you?
An aortic regurgitation. Now, some people may just refer to it as an aortic regurg. And that's when your aortic valve doesn't close properly. So yes, okay, a lot of flow back. Okay. But normally speaking, yes, okay, flow reversal, there's nothing wrong about it. Okay. But just think of it that, okay, if we had a positive Doppler shift, okay, this is okay as the max of the systole of the heart. But then your heart goes into diastole. At this slight negative Doppler shift in this case here is going to be as okay of the diastole. So that's normal. Likewise, that's okay. If you could have had okay as a negative Doppler shift. Every time it says okay, this is going to be as okay your max negative Doppler shift, which is going to as okay be at as okay just at end of systole of the as okay or peak of your systole. Maximum contraction of the heart. Where okay, when it goes into relaxation, this small is okay, that's going to be as okay you were flow reversal, which mainly means, okay, in this case, okay, the heart goes into diastole. Right. But whereas I just said, if this here is okay, it becomes too great. Negative. Or we can say, okay, this becomes too high positive. Then, okay, it's too much good is bad. Okay, sorry, girls. I didn't mean to take you there. That's for your scanning modules to deal with. But anyways. Anybody else? Anybody else want to say something? Anybody else has a question? Yes, ladies.
I don't have any questions right now.
You okay?